All right, let's begin. We're talking about the Bernoulli equation today. This is one of my favorite lectures of the semester. I really enjoy Bernoulli's equation because typically students have some familiarity with the concepts. A lot of times it's something that people have heard of by going to like a children's museum or maybe a little bit in physics. But there are so many interesting and important applications of Bernoulli's equation that it's always exciting to go a little bit further into depth. So your next assignment, homework number 6, which includes some additional Euler's equation problems and Bernoulli's equation problems, is due before class on Tuesday. Now, you had a recorded lecture video on Tuesday, and I think that there was the Euler's equation in 2 dimensions in that lecture. And if I am remembering correctly, your homework assignment has Euler's problems in 2 directions, and so the lecture will be important for that. And whenever I give Euler's equation on a test, I would never do it in just a single direction. So you need to be able to find the change in pressure that will occur when something is accelerating both horizontally and vertically at the same time. And you will see an Euler's equation problem on an exam. I don't know whether it will be exam 2 or the final, but it's very, very uncommon for students to escape without being tested on Euler's equation. Any questions related to announcements or schedule type stuff? No? All right. Before we talk about Bernoulli's equation, let's watch a couple of videos related to laminar flow. Not that there's any necessary connection between laminar flow and Bernoulli's equation, but I've just dug up some interesting videos that I think are worth taking a moment to watch. And so let's do that. All right, so we watched these 2 videos. And now let's move on to Bernoulli's equation. Now, a bit of background. Remember, we've looked at this slide before when we first introduced Euler's equation. And so let's compare and contrast. Euler's equation, hold on, I'm turning it to cool. It feels a little stuffy in here. Euler's equation was talking about how local acceleration changed pressure and elevation. And it could be either one of those things that's changing, sometimes both. You know, if it's an open container that's being accelerated, then the liquid surface may be tilted as a function of how much acceleration is occurring. And so this local acceleration changes of velocity with respect to time is unsteady flow. Bernoulli's equation is related to non-uniform flow. So that's changes in velocity with respect to position caused by convective acceleration. So there's a couple of different ways that we're going to be writing Bernoulli's equation, and this one has units of length. Each one of the terms would have units of feet or meters, and this is called pressure head, elevation head, velocity head. And in civil engineering, it's most common for us to write Bernoulli's equation in this form, although there are other variations of it where we would multiply each term by gamma. The Bernoulli equation comes from using Euler's equation at the starting point and applying it when conditions are steady and using just 2 points along a streamline, and then making the assumption of it's being applied to a fluid that's incompressible and inviscid. Now we need to talk about these 4 assumptions because they're really important in understanding the situations where Bernoulli's equation does an okay job, and there are other situations where Bernoulli's equation actually doesn't describe the change in pressure very accurately. So we'll talk about those assumptions. But first, let's just review the idea of a model. And you were probably first exposed to the idea of engineering models in Engineering 104. The idea of a model is that sometimes it pays for us to represent reality with a simplification. And it can be a variety of things. It could be an equation that is representing reality, or it could be a physical model. And so it maybe is a scaled model of an airplane that goes into a wind tunnel, and we use that model in order to make small changes and then understand how those adjustments would affect the behavior of the full-size prototype. So for obvious reasons, it's much cheaper and easier to change the wing shape on a model that's only 2 feet long than on a full-size prototype that's hundreds of feet long and costs millions of dollars. And so these models are useful simplifications. You can see that this isn't the same thing as the prototype. You know, for instance, it hasn't been painted the same as the prototype. So it's not a perfect representation, but it doesn't really matter that it's not painted the same. I mean, very, very slightly, the paint type is going to have an effect on the aerodynamic performance of an aircraft, but not enough to really matter. So sometimes it's okay if our model doesn't match reality perfectly. You know, another variation is you can see that it doesn't have the windows. Okay, maybe that doesn't really matter so much. So, but it does have the engine mounts. Even though the model doesn't have working engines inside, it wouldn't be accurate enough if they just had the wing without the engine mounts. And so they've gone to some trouble to represent some things, but then they've let other things slide. There aren't miniature humans inside, for example. So now the same thing is true about numerical models. Sometimes numerical models are derived from the fundamentals of physics, and they have a theoretical basis that can be proven from first principles. And the Bernoulli's equation is one of those, where it's going to be dimensionally homogeneous. And dimensionally homogeneous means that on the left-hand side of the equation and the right-hand side of the equation, the units match up. And that this is derived from the first principles of physics. And in contrast to that, a fundamental equation that's dimensionally homogeneous, sometimes we have empirical equations that aren't dimensionally homogeneous. And you can sometimes spot an empirical equation because it'll have just these correction factors or coefficients that don't really seem tied to any kind of physical constant. What they are is just their curve fitting coefficients that come from observation. So for instance, if we wanted to predict the range that an aircraft would have, maybe two important components that could be used to predict range would be how much fuel is on board and the weight of the aircraft. And those aren't the only two components, but maybe this simplification of reality is good enough for whatever use it's going to be applied to. You know, maybe it's a close enough match where the 2 or 3% difference isn't so significant compared to the simplicity of using this equation. So there can be a reason to use an empirical equation even when it doesn't perfectly represent reality. And the way that these factors would be identified is if you took Excel or some other program and you did a plot of the range versus the other parameters. You can have a multivariable regression and identify these coefficients with just the process of experimentation and observation. Now in engineering models, there's some terminology that's useful to understand, and the idea of a boundary is that it defines the system, and the system is the objects and the fluids that are being studied within some boundaries that are being tracked. And within the wind tunnel, for example, would be our control volume. The system would be the model and the fluid that's going over the model. The variables are those parameters that can change, and often we have certain inputs that we intentionally adjust to try and see what are the reactions to those varied inputs. And so in the case of a wind tunnel, we might want to adjust the velocity of the gas that's passing over the model. Maybe we would change the pressure of the atmosphere that's inside of the wind tunnel to represent what's happening at higher altitudes versus lower altitudes. And then the parameters are system elements that don't change. Constants like the gravitational acceleration or the density of a fluid or the viscosity of a fluid. Now, these constants can vary with the variables. And so, for example, the density of air is different at 30,000 feet than it is at sea level. But the density of air at sea level for a given temperature is going to stay constant. And so this is just to distinguish between some of the terms that you'll see when describing engineering models. And so the Bernoulli's equation is a model, but the reason why I talk about this discussion is because, in the lab this week we did a Bernoulli's equation experiment, and you already saw with your own eyes that that the little model that we had doesn't, it's not perfectly described by Bernoulli's equation, because that last tap, the water level didn't rise to the same height as the first tap. And that's because one of the assumptions that Bernoulli's equation has built in. So remember, the 4 assumptions for Bernoulli's equation is it says that the sum of the kinetic and piezometric pressure is constant along a streamline when flow conditions are steady with a fluid that's incompressible and has no viscosity. I think on an earlier slide I described that as being an inviscid fluid. An inviscid fluid is one with no viscosity. Okay, so let's talk about Bernoulli's equation. Now, along a streamline, we've already talked about what streamlines are, and if I was going to draw a pipe section that is going from large diameter to small diameter. And so this is a nozzle that's contracting, so the water velocity is slow, but we have a streamline that just kind of shows the direction of the flow, and as it contracts, these streamlines are coming together, which is an indication of acceleration. But Bernoulli's equation is applied along a streamline, and so you pick a couple of points. Maybe we would want to apply Bernoulli's equation starting here. If this was our location 1, then we couldn't use Bernoulli's equation to find out what is the pressure and velocity down here, because that's on a different streamline. And so we would have to choose the same streamline in order to identify our location 2. And what we ordinarily do in practice is we use the center of the pipe, because the advantage of using the center of the pipe is that sometimes these pipes are horizontal and Z1 equals Z2. A lot of the time pipes are horizontally oriented. Think about the pipes that are under the road that carry water. Those are effectively horizontal in a flat town like Huntington. It needs to be really a steep place before the elevation difference would be meaningful. So first equation, along a streamline, that's what I mean, is you're using the center line of the pipe for location 1 and location 2. And what Bernoulli's equation is going to do is it's going to predict how the pressure changes between these 2 points. Steady flow. Who can refresh our memory what steady flow means?
The velocity isn't changing.
The velocity isn't changing with respect to time. Very good. That's right. So it means that the valve is not, that the valve that controls flow is not being opened or closed, that if we look at this picture a few minutes from now, the velocity will be the same as it is now. So conditions are not varying over time. So steady along a streamline. Okay, incompressible fluid. The fluid can be broken down into 2 primary categories. There are liquids and there are gases. There's also plasma, but we won't talk about plasma in this course. We'll just talk about liquids and gases. So between liquids and gases, which of those is better at being incompressible? Liquids. I mean, gases are definitely compressible. We all know that. But liquids are only a little bit compressible. I mean, they're kind of compressible. Early in the semester, we had a lecture where we talked about the compressibility of water and how its volume changes just a little bit when pressures are up in like the 10 to the 9th pascals. It'll change a few percent if you really, really hammer down on it, but not much. And so what I'm saying is that Bernoulli's equation has these restrictions. Like, it's going to be accurate when you follow these rules. The further away you get from following these rules, the more Bernoulli's equation is going to have some errors in predicting what's actually happening. Okay, so you can use Bernoulli's equation for a gas, but gases are compressible. So you're kind of violating the rules there. You're not going to get perfect performance with Bernoulli's equation if you use it like if it was a gas going through a metal pipe. So, earlier I think maybe I'd said water was flowing through the pipe. What if it's air? Air flowing through the pipe. So one of the reasons that Bernoulli's equation isn't going to give you a perfect idea of how the pressure changes as air goes through the pipe is that the air can be compressed. And Bernoulli's equation doesn't have anything in it to account for that compression of the fluid. It's only handling the effect that occurs due to convection, convective acceleration. So does everybody understand the implication of this incompressible assumption? It's a rule that we can't always follow. So water is pretty good at following this incompressible rule. Gases, less good. Let's think about the last rule though here. A fluid that has no viscosity. Can you think of a fluid that has no viscosity? If you open up the appendix in the back of your book, I don't think you'll find a fluid that has no viscosity. The viscosity of water is much higher than the viscosity of gases. And you know that just by walking through those two different fluids. Like when you walk through water in a swimming pool, the water is getting out of your way very slowly. That's what makes it hard to walk through water. You can't run through water like you can run through air because the water is resisting your movement because of its viscosity. So water is a viscous fluid. It has viscosity. Air is a little bit better at being inviscid. It's not perfectly inviscid, but it certainly deviates less from the assumption. So basically what I've told you is that water isn't good at following the rules when it comes to the no viscosity part of it, and air isn't good at following the rules when it comes to the incompressible part of it. So there's no fluid that perfectly follows the assumptions of Bernoulli's equation. So that would mean that it's never a perfect representation of what's actually happening with the pressure. But that's okay. We don't need perfection. We can still get useful information from Bernoulli's equation under situations that are appropriate. And so those situations that are appropriate is if the 2 points are relatively close together. If they're relatively close together, then you're not going to see much of an effect due to pipe friction. And that's what the inviscid assumption is all about. The fact that the fluid has no viscosity. If the 2 points are close together, then there's not going to be too much pipe friction, and it doesn't matter that the fluid has viscosity. And it's okay that you use Bernoulli's equation with air, because air doesn't always compress that much. If it is just a modest compression, then there won't be too much of a change in pressure due to that. So here is the representation of Bernoulli's equation where we've divided each term by gamma. And so here, each of the terms has units of pascals, or newtons per meter squared. The other way that we've seen it before, this bottom version of it is more useful in civil engineering applications where maybe we need to calculate pressure heads and use the different elevations of tanks in order to understand changes in pressure. So these are both the same equation. It's just the one on top, if we divide each term by gamma, then we get the one on the bottom. And it may not be immediately obvious for this velocity head term, but if you have density and you divide by gamma, then remember gamma is density times g, right? Gamma is density times g. So if you take this term, which is density times velocity squared divided by 2, and you divide it by gamma, then all that's left over in the denominator is g. So this kind of a nozzle type problem, which we looked at previously just when we were doing some calculations to quantify convective acceleration, this is the kind of scenario that we'd use Bernoulli's equation on. Someplace where a converging or diverging section is causing a change in velocity with respect to position. We want to know how the pressure is going to change. And that's what happened in the lab on Tuesday, is we had water that was moving with a slow velocity, and it sped up because the diameter of the tube that the flow was going through decreased. And what did you remember seeing? The little piezometer tubes that went up through the pipe, how did the pressure change in the throat where the diameter was lower? It was smaller, right. So the liquid level was lower down here because in order to have higher velocity, what this is saying is that if location 1 is here where it's 10 meters per second, and location 2 is where it's 20 meters per second, and you can see it's horizontally oriented, so Z1 equals Z2. Without doing any calculations, just consider the equation qualitatively. If you had some certain pressure at 1, and you know the velocity at 1 is 10, and now the velocity at 2 is 20. So that means that this velocity head term is going to be bigger. But the sum of the left-hand side has to equal the sum of the right-hand side. And so you've had pressure and velocity head at 1, and now velocity head went up at 2, so that means that the pressure has to go down. If we say that the sum has to equal some amount that was fixed on the left, if velocity head goes up, pressure head goes down. So let's get a feel for that. These calculations, our first attempt to substitute things into Bernoulli's equation. Let's say that we have a certain section where we know the velocity at 1 and 2, and that's given on the screen. And we know the pressure at 1 is 400 kPa. We want to determine the pressure at 2. And this is water, and so we know that the unit weight of water is 9810 newtons per cubic meter. So I'd like you to calculate P2 using Bernoulli's equation. All right, so before we actually put the numbers into the equation, it may be useful for us to consider, what we expect directionally to occur. And then that is useful when you calculate your final answer to have an idea of whether it's reasonable. You always want to know if your data is passing the reasonableness check. Okay, so the pressure at 1 is 400, and that was where the velocity was fast. And so if the velocity is decreasing, that energy that used to exist in the velocity head has to go somewhere else. Because velocity head, remember, is v squared divided by 2g. So what we're saying is, here at 1, there was quite a bit of energy in the velocity head, because 5.5 meters per second is really moving along quick. So what direction is the pressure going? Is the pressure going to be higher than 400 kPa, or lower than 400 kPa here at location 2, just based on not necessarily the calculations, but just our intuitive understanding of what Bernoulli's equation says.
It's going to be higher.
It's going to be higher because that energy's got to go somewhere. It's not going into elevation because the pipe is horizontal. So the only other place that that velocity head can go is into the pressure. So the pressure will be greater than 400,000. So now, with that in the back of your mind, you'll be able to assess the value that you calculate and know at least if it went in the right direction. So let's look at how we set this up. So here's Bernoulli's equation with the three terms, pressure head, elevation head, and these first two terms together, collectively we can think of as potential energy. And then the last third term, we can think of that as kinetic energy. At 1 and 2, the elevations are the same, so that just drops out of the formula. And if we rearrange it to solve for P2, which is what we're trying to find, the absolute pressure, well, I don't know if it's absolute or gauge, but what I mean is we're not necessarily solving for the difference in pressure between the 2 points, but we want to know, based on the known pressure at 1, what's the known pressure at 2. So rearranging this equation algebraically, the pressure at 2 is going to be the pressure head at 1 plus the velocity head at 1. So the total amount of energy at 1 minus the velocity head component at 2, and then multiply that by gamma, and it'll give us the pressure. Okay, so making the substitutions, and I really think it's a worthy investment to take the time and write in not only the formula, but then the substitutions themselves, including units, because it's just far too easy to mistakenly put in 1,000 when really you should have used 9810. It's too easy to mix that up, but you're less likely to make the mistake if you also write the units. Because if you wrote 1,000, then you'd have to also write kilograms per cubic meter, and then you'd see those kilograms and you'd say, oh wait, it shouldn't be kilograms because I've got newtons in the numerator. I need newtons in the denominator as well. So that's kind of part of the reason why I think it's worth the extra effort of writing in the numbers and the units, is that you'll find and avoid mistakes that you'd rather not make. Okay, and then here's the intermediate quantities where I've found out the head that's tied up in each one of these terms. And so we've got 40.775 meters of pressure head at 1 and 1.54 meters of head that's in the velocity. So between the two, most of the energy is in the pressure. I mean, there is some energy in the velocity head, but by far the lion's share of the energy that's in the fluid is as pressure right now. So the sum of those two, the pressure head and the velocity head, is the total amount of energy that's at 1, and we subtract out this minuscule amount of energy that will be tied up as velocity head at 2. The flow is going 0.63 meters per second. There's hardly any energy tied up with that velocity. So the bulk of this energy is going to be in the pressure. And so the pressure at 2 will simply be 9810 newtons per meter cubed multiplied by the sum of the pressure heads, and that ends up being 415 kilopascals. So that matches our initial expectation that the pressure would go up. The velocity head is pretty meager, so just instinctively, if we saw that it went up to 800 kilopascals, it would be in the right direction, but I'd be skeptical just because I know that there's usually not that much energy in velocity head. It's usually a pretty small fraction of how much energy is in a system. In a lot of cases, we'll just neglect the velocity head. In Chapter 7, when we use the energy equation to finally get over this hurdle of not being able to account for the effects of pipe friction, that inviscid assumption that we have built into Bernoulli's equation, finally we deal with that in Chapter 7 when we start accounting for the effects of viscosity. And when we do, what we'll find is that pressure changes due to pipe friction are so much more than the pressure changes having to do with a change in velocity that it's kind of pointless to even keep track of changes in velocity unless you're really being precise and it's like a really flat pressure network over a very long distance. Most of the time just it's the head losses that are so much more important than pressure change due to velocity adjustment. So any questions on this first use of Bernoulli's equation? Seems straightforward enough. Now, this is another concept that I introduced briefly on Tuesday. I didn't have a lot of energy on Tuesday. I was hurting that day, so we didn't get much chance in the lab to go over the details of this. But I hinted at the idea that for a converging section, if you've got a non-compressible fluid, that there's no potential for storage inside of this system. Whatever flow goes in has to go out. Once it's full of water, there's no extra storage tank here that can take extra flow. So it's full of water, you put in 1 more liter, then that's going to force out a liter from the front of the nozzle. So a liter in equals a liter out. And if there's no storage, then what that means is that the flow rate, Q, which has units of liters per second or cubic meters per second, the flow rate in and the flow rate out are equal. Now, consider a pipe section that has a known diameter at the inlet and at the outlet. So they can be different diameters. We can calculate the cross-sectional area from the diameter because the area is pi d squared divided by 4. I'm surprised I don't have, oh, there it is, right there on the slide. Pi d squared divided by 4 gives us the cross-sectional area. And so the flow rate at this location 1, the inlet, would be whatever the velocity is there multiplied by the cross-sectional area. And so if the flow in and the flow out are equal, then what that means is that A1 times V1 is equal to A2 times V2. So at 2, the area is less, therefore the velocity has to be higher. This is the equation that you'd use in a problem like this if you weren't given the velocities. So in the homework, maybe I give you one with the velocities given, but more likely what I did is I told you one of the velocities, but both of the diameters. So if you know both of the diameters, then you could find out what is the flow rate, and then you could find out what is the velocity at the location where the velocity wasn't given. So you'd use this formula. It's called continuity, and really you don't start learning about this formula until chapter 5, but this is a sneak preview because it really does closely relate to Bernoulli's equation. And we're going to use it with this example. Okay, so we have a converging pipe section, and it's a gas that's flowing through it. We have a differential manometer that's using a different fluid inside the differential manometer. We've seen this before, for instance, where we used mercury in a differential manometer because the advantage of that was that there would be less of a deflection compared to if you had a less dense fluid. This is a little bit strange though, because in the previous examples where we used a differential manometer, I don't know if you remember it, but let me just do a quick sketch on the whiteboard. In the previous times we've seen a differential manometer, there's been a pipe, and let's just make this one horizontal for argument's sake. Okay, and it connects back up, and what we saw was that the liquid level was, let me just remind myself, it was like this. The liquid level was lower on the left as compared to the right. So this is what we saw in the example of water flowing through a horizontal pipe, and it was flowing from left to right. And what this differential manometer, since it's horizontal, there's no pressure difference due to elevation changes, but the pressure difference here was because of pipe friction. So what we were seeing is that there's more pressure at 1 compared to 2. There's more pressure, and that's what's causing this delta H. Like it was pushing harder on the left. So think about that there's more pressure at 1, and so it's pushing harder on the left side than the water is pushing on the right side. And so that causes the manometer fluid to be deflected downward on the left. So this is what we saw before. Now look at the differential manometer on this screen. So where is there more pressure? On the right, because the liquid level is lower on the right side of that manometer. So the pressure is higher on the right. So let me explain to you what's happening here. At 1, the velocity is low and the pressure is relatively high. Then this converging section is speeding up the air, and so the velocity is increasing and the pressure is decreasing. But then at this opening of the tube, the air stagnates, and there's a streamline that just dead ends. And so the air goes from having a high velocity to 0 velocity. And so what happens is that right at the opening of this tube, all of the energy that existed as velocity head is suddenly transformed into some additional pressure. So that's why the pressure is higher inside the right side of this differential manometer tube, is because of the stagnation point. Inside of this converging section, the pressure is lower, but this is measuring, in the tube, is measuring not only the effect of the pressure, but also the effect of the velocity head. So we can use Bernoulli's equation here in kind of an interesting way to quantify the velocity. And let me just walk you through it. Let's say that we know the area here at location 1 is double the area at 2. So that's, I'm not saying the diameter, I'm saying the area. So if the area at 1 is double the area at 2, then that means that the velocity at 2 is double the velocity at 1. How does that follow? Just remember on a previous slide, A1 V1 equals A2 V2. Because this is a Q in equals Q out situation. So Q at 1 equals Q at 2. So A1 V1 equals A2 V2. And so if the area at 1 is double the area at 2, 2A2, then we're saying V2 is double V1. A2 divided by A2 V2. So the velocity 1, which, well, oh, I forgot the V1 term there. V1. So 2 V1 is equal to V2. Right. You have to have double the velocity when the cross-sectional area is half. So it's air flowing through the duct, and we're going to assume that the air doesn't have a change in density as it flows through the duct, because that's what Bernoulli's equation expects. It expects that it's an inviscid, incompressible fluid. So if we wanted to know what's the velocity at 2, we can use this deflection in the differential manometer to predict it. And so what we're going to do is use both Bernoulli's equation and also the manometer equation. And so right now, we don't know P1 or P2. That's not given. So let's think about how many unknowns do we have. We don't know P1. What about Z1 and Z here inside the tube? The elevation is the same. And by the way, we're going to apply Bernoulli's equation can, as long as we're talking about the same streamline, it can be applied at several locations simultaneously. So here's the nozzle. It chokes down. And then here's that tube. So here's location 1. Here's location 2. And then here's what I'm going to call location T. So it's all along the same streamline. So P1 divided by gamma plus Z1 plus V1 squared divided by 2G. Here is Bernoulli's equation. On the right-hand side it says 2, right? Let me just paste this in real quick so we can look at it. See how right here it says 2 for each of the terms on the right-hand side? It could also say T. So as long as you're on the same streamline, the energy at 1 is equal to the energy at 2, and that's equal to the energy at location T. It's just what form the energy exists in is being exchanged. You're having less velocity and more pressure at T compared to 2. So think about what was happening. At 1, there's more pressure and less velocity. At 2, there's more velocity and less pressure. But then at T, there's no velocity because the wind just kind of stops at that open stagnation tube. So all of the energy that existed as velocity is now tied up as extra pressure. So that's here, this formulation of Bernoulli's equation where it's saying P sub T divided by gamma plus T, Z sub T and so on. Don't be confused because it used to say 1 on the left and then 2 on the right. Bernoulli's equation can be applied at multiple locations simultaneously. So that's what we're going to do. So what's known and what's unknown? Okay, so at 1, we don't know the pressure. We're going to ignore the velocity, so the elevation. So Z1 equals ZT. Z1 equals ZT. So that cancels out. So all that we're really left with is, let's simplify Bernoulli's equation. It's P1 divided by gamma plus Z1 plus V1 squared divided by 2G is equal to, oh wait, we canceled out Z1, so I'm going to erase that. So it's just P1 divided by gamma plus V1 squared divided by 2G is equal to P sub T divided by gamma. And I'm not going to write the elevation because the elevation at 1 at T are the same. And what's the velocity inside of the stagnation tube? 0 velocity. That's the definition of stagnation. Remember that inside of those tubes, conditions are static. So there's no fluid flowing inside of this tube. It comes to an equilibrium and stops. So the water deflects, and so then it stops moving on account of the difference in pressure, and then all of the air inside of the tube is motionless. So the air runs into the tube and stops. There's just some air that's stuck there. And then inside the tube there's no motion. And so the reason why I bring it up is that V sub T is 0. So I don't even write it. So here is Bernoulli's equation. Bernoulli's equation is just P1 divided by gamma plus V1 squared divided by 2G is equal to P sub T divided by gamma. So this is the simplified Bernoulli's equation. Now what do we know in that? We don't know V1. and we don't know PT, and we don't know P1. But this manometer will tell us the change in pressure. So the change in pressure between T and 1 is reflected by the manometer equation. So the manometer equation is effectively telling us that the P1 plus delta H times gamma is equal to P sub T. This is the manometer equation. All right, so I'm going to pause for a second. And what I'd like you to try and do is combine the manometer equation and the simplified Bernoulli equation to find out what is the velocity at 2. Because previously we were saying that there was effectively 3 unknowns in this formula because we didn't know pressure at 1, pressure at T, or the velocity at 1. But this manometer equation can be rearranged to find the change in pressure between the 2 points. So I'm going to pause for a second. Let's see if you can substitute those 2 things together to find out V2. Okay, sometimes it makes more sense once we plug some numbers in. I've rearranged the manometer equation to, on the left-hand side, it's saying the change in pressure. On the right-hand side is just delta H times gamma. So the change in pressure between the tube and location 1 is going to be 0.1 meters of water, 9810 newtons per meter cubed. So that is a pressure change of 981 newtons per meter squared. So now that we've got that number, you can see in Bernoulli's equation, all we need to do is multiply each term by gamma and then rearrange the equation to solve on one hand side of the equation the change in pressure. And we know the change in pressure. The change in pressure is 981 pascals. So let me bring those calculations up on the screen for the benefit of those who may be watching a bit later. Just with the preliminaries here, with the density of air given as 1.2 kilograms per cubic meter, then we could calculate the unit weight of it by multiplying by G. And then the fluid properties of water are applicable because of this manometer being filled with water. So the basic concept here, the principle, is that all of the energy that's in the fluid at 1 is still there at 2. It's just changing its manifestation. It's changing from more pressure to relatively more velocity head at 2. And then at location T, it's changing. The form of the energy changing at T is that all of the velocity head that was there before is now exchanged into additional pressure. So the elevation is the constant for each of them, but the pressure is going to be changing. So the manometer equation is what we use to find out the difference in pressure, 981 pascals. And then Bernoulli's equation, which we had canceled out the terms that didn't apply, like the elevation, and there's no velocity in the tube. So this time we're going to want to use the form of Bernoulli's equation where we had multiplied each term by the unit weight, and then we can further rearrange it to have P sub T minus P1. So if we move the P1 over to the right-hand side of this equation, then we're going to get that the change in pressure is just density times the velocity at 1 squared divided by 2. Okay? And you can see that ultimately what that means is, if you want to rearrange it algebraically just to solve for V1, the velocity at 1 is 40.4 meters per second. So, at first glance, it wouldn't have been obvious that you could find the absolute velocity at 1 when there was so much we didn't know. We didn't know the diameters. We didn't know the velocity at 2 or 1. But that deflection and the simple fact that there's a stagnation point, that's really the other thing that is known, is that V inside of location T is 0. So having that known velocity simplified Bernoulli's equation so that then there was one less fewer term and unknown, and we could solve for the velocity at 2. Yeah, by the way, now that we know V1, we could find V2 because it's known that V2 is double V1. That was one of the initial givens. Any questions from this second Bernoulli's example? All right. So you've got homework you're working on. Feel free to stop by my office if you'd like to talk about it, or call me on Teams, or send me an email. That's it for today. I will see you next Tuesday.